Hey guys, it's chapter 6, part 2. So I'm picking back up on slide 8 of the PowerPoint. So we've already been through talking about the types of light. Again, I mentioned the speed of light, letter C, is going to be around 3 times 10 to the 8th meters per second. That is a constant value. All types of light travel at the same speed in a vacuum. Okay, so this is the speed if light is traveling out in space, like from the sun to the earth, this is the speed that it travels. Now, if light enters into a more dense medium, like when light actually goes from outer space and enters our atmosphere, it actually slows down a little bit. Now, the difference between outer space and air, the difference is pretty small. We're not really going to worry about it in chemistry, but if you take physics, then they're going to tell you a different value for the speed of light, and as it passes through air, as it passes through water, or any other substance, you do get different values, but this is the only number that we're going to use in this class. Okay? So, we have lots of different types of radiation. Each type of radiation, and I'm talking about the picture on the previous slide, each one has a different wavelength and a different energy that we need to be able to relate and calculate. The wavelength, as I said before, if we're going to do calculations, the wavelength has to be in meters. But since the values change so much, the wavelength is not always going to be given to you in meters. Sometimes they're going to give you the wavelength in kilometers. Sometimes it'll be in centimeters. Sometimes it might be in nanometers. So you have to be able to make adjustments based on that. Okay, so with all our different units, you have to go back to chapter 1, make sure that you know your prefixes, and you need to be able to quickly convert from whatever unit that's given, be able to convert into meters before you start plugging in your calculations. All right, so we have a question. The color on the slide is not very good right now, but I'll read it. Visible light has a range of wavelength from 400 nanometers to 700 nanometers. That's important for you guys to know, okay? Now, wavelength and energy are inversely proportional. So, if the range of light has wavelength from 400 to 700, the side with lower wavelength, the 400, that's going to be the end of visible light that had more energy. That's violet. So violet light has a wavelength close to 400 nanometers. At the other end of the visible section, red light has a wavelength of 700 nanometers. Okay, so again, that is important stuff for you to know. Violet light, the wavelength is around 400, red light 700. It's actually a continuous spectrum in between, meaning when I say red light has wavelength of 700, it's not actually a specific number, it's a range. If your wavelength is anywhere from like 650 to 700 nanometers, that's all going to be red, but there are different shades of red. As I go to lower wavelength, get down near 650, the red is going to slowly turn into orange. And then as I keep changing the wavelength, then the orange is going to turn into yellow. Okay, so we're going to have different shades of red and different shades of orange as you move through the different wavelength ranges that we talk about. Okay, same thing on the violet end. From 400, when you get up to 430 or 450, you're going to get into indigo and blue, and it's going to kind of slowly blend. It's not a specific change that happens suddenly from one color to the next. So when we talk about red light, you have to realize there's a lot of different shades of red light. So if you want to specify, you'd have to actually give the specific wavelength that you're talking about. All right, so the question says, calculate the frequency range for visible light. So it gave me the wavelength. I want the frequency. So I would look at my equations on the board, and I need to find an equation that has wavelength and frequency in it. The only equation up here that has wavelength and frequency is the first one. If I know the wavelength, c is the speed of light, which is a constant. That's 3 times 10 to the 8th. So I can plug in the speed of light, I can plug in the wavelength, I'm going to solve for the frequency. So I'm going to have to do it in this problem, I'm going to have to do that twice, okay? Because it gives me 2 different wavelengths that cover the range. So when I get the frequency, again, I'm going to have to convert each wavelength into a frequency value. So to do that, I'm just going to plug into the equation. Again, it's been rearranged, but there's my equation right here. I'm solving for frequency, so they went ahead and divided the wavelength over, and it's the frequency equals speed of light over wavelength. Plug in my speed of light right there. But my wavelength, notice this is not the wavelength they gave me. They gave me 400 nanometers. Before I plug it in, you have to convert the 400 nanometers into meters, which should give you 4 times 10 to the minus 7 meters. Then that number gets plugged in right here. Divide these two. Be careful with your parentheses and your powers of 10. And you should get that the frequency in the base unit of hertz is going to be 7.5 times 10 to the 14th. So that's the frequency of, we said 400 nanometers, that's my violet side of the range. So the frequency of this violet shade is going to be 7.5 times 10 to the 14th. I can then do the calculation again for the red side, which is going to be my 700 nanometers. Set it up the same way, speed of light over the wavelength to get this frequency. Now notice the second problem had a higher wavelength, but we said wavelength and frequency are inversely proportional. So the one that had a higher wavelength actually gave me a smaller frequency value. When one goes up, the other one goes down. All right, now, so we know now how to do some basic calculations with light, but now we need to talk about, okay, how does this apply to electrons? All right, so as you know, and this is in the early 1900s, in the time of Einstein and Niels Bohr and a lot of those guys, you know, really brilliant physicists and chemists and mathematicians. There were a few observations that were made that kind of told scientists that the theory of light and how light travels and how it interacts with matter, there are specific rules that have to be followed, okay? And some of the things that help them figure out what those rules are, there are 3 kind of separate experiments or observations that you need to know about. First one is black body radiation, which is basically if you take an object that's made of like a pure element or a pure compound, and if you heat it up slowly, just heat it up higher and higher and higher, when it gets to a certain temperature, it'll start to emit light. So it'll start to glow and give off light, okay? Well, the fact that it doesn't give off any light until you get up to a certain temperature tells you that there's a certain point where if the electrons get enough energy, all of a sudden they can start changing their orbital levels and go from a low energy orbit to a high energy orbit. And when they start shifting the orbitals, something weird's going on there. So all of a sudden the electrons go from kind of being locked in their orbits. When you give them enough energy, then they can jump into other orbits. And when they jump up in other orbits, when they come back down again, that's when they emit photons of light. Okay, we'll talk about that more as we go. But that idea was very important in telling scientists that electrons can't really shift back and forth between orbits anytime they want to. They have to have enough energy to jump from a low energy orbit to a high energy orbit. And if there's not enough energy present, then they can't do it. Okay. The next one is called the photoelectric effect. If you guys know about Einstein, you know, he came up with a theory of relativity. He did all kinds, you know, E equals MC squared. He did lots of important things during his scientific career, but he actually won the Nobel Prize for the photoelectric effect. So that's a very important topic. Again, there's a slide coming up where we'll talk about that. And then finally, when we have a light bulb that's filled up with a gas, like a neon light is a light bulb that's filled up with neon gas. When we turn the light bulb on and send electricity through there, it makes the electrons start jumping up and down in their orbits. And we get, instead of getting a white light that contains all the colors of the rainbow, when we turn on a neon light, we don't get all the colors. We only get certain colors coming out. And again, that's really important because what it shows us is that electrons can't just jump up and down in whatever orbitals they want to. There are only certain ones that are allowed, okay? So these 3 concepts that we're gonna talk about a little bit more are all very important in kind of laying the foundation for how we how we learned about how light and electrons start to interact with each other. So, the black body radiation is what this slide's about. Again, it's a little physicsy, so I would like for you to kind of read in the book where it talks about black body radiation a little bit. If you're not sure about it, look it up. Just get a simple explanation for it, so you know kind of what it's about, and then you can move on from that. Then we get into Max Planck, German scientist that he basically came up with the theory that energy comes in little packets. Okay, so instead of light being a continuous wave, he thought that light was traveled in packets or little packages, where a burst of light would travel, and when it hit you, if you absorbed it, there's a specific amount of energy that could be absorbed from each packet of light. So the smallest amount of energy you can have is called a quantum. The plural of that is quanta. So each packet, if you absorb 10 of them, that'd be 10 quanta. And if our quantum of energy is in the form of light, then we call that a photon. Okay, so the term quantum and the term photons are related to each other. It's just photons are specifically referring to a packet of light energy. So Planck came up with the idea of quanta, then Einstein used the idea of quanta to explain the photoelectric effect, which basically is if you shine a light onto a metal surface, like sodium or something, if you give enough energy to the electrons that are in the atoms of the surface, if you give them enough energy, you can make those electrons, instead of orbiting the nuclei, if you give them enough energy, they'll fly away. Okay? Well, the weird thing happens that if light was a continuous wave, then you should be able to take any source of light, and if you increase the intensity of the light enough, then the energy going to the electron should just get bigger and bigger and bigger. When it gets enough, the electron should be able to fly away. That doesn't happen. The only way you can actually get the electrons to fly away, if I start out with a low energy light bulb, like where the color of the light is on the red end instead of on the purple end, it doesn't matter how bright the light is, you'll never get the electrons to fly out. But if you increase the energy by decreasing the wavelength, so shifts from red light to like yellow or green or blue or violet, if you go to a color that's more energetic, all of a sudden what will happen when you get to the right level, the electrons in the surface will start flying out. So you can make that happen by increasing the energy of each photon, but it doesn't help to just increase the overall intensity of the light bulb. That principle, that difference between the two, told scientists that, okay, the electrons must, if they're in one energy orbit around the atom, if you want them to jump into a different orbit, they can't absorb multiple photons or a continuous wave of energy. It has to be one burst of energy that gets it all the way up to where it needs to be. Whether it's going to jump to a higher orbit or if it's going to escape the atom and fly away, it has to be one single burst of energy. And if that one burst it absorbs doesn't have enough energy to get it where it wants to be, then it can't absorb the energy at all. It doesn't have either way to go with that. Okay, so that's Einstein's photoelectric effect. Then we get into the calculations. If the energy is related to the wavelength and the frequency, then that means that we should be able to do some calculations. So again, I've already shown you some of the equations, but you can derive a relationship between energy and wavelength, E equals hc over lambda. We also, I think on the previous slide, it was E equals h times nu. Those are both fundamental equations that we need to know about. So then we should be able to do a calculation. So, question asked, calculate the energy of a photon that has a wavelength of 430 nanometers. So they gave me the wavelength. I want the energy. Again, we look at our equations and say, where's an equation that has wavelength and energy? It'll be this one right here. Now the 430 nanometers is my wavelength, but I need to convert it into meters first. So change nanometers to meters. Okay. Once you do that, you can plug it in, plug in H and C. Now H is Planck's constant. I didn't say it out loud earlier, but it was on the slide. Planck's constant is 6.626 times 10 to the minus 34th joules seconds. So if I plug in Planck's constant, speed of light, and wavelength, check all my units. Everything should cancel out except for the joules. So my energy, when I get my answer, should be in joules. Okay? I'm not going to finish that calculation because I think you should be able to handle it. I'm going to cut the video, and the next slide or next video will pick up on the next problem.